Good afternoon, class. Here's exam 3. A review covering chapter 3, differentiation rules, chapter 4, applications of differentiations. And in this part, we're going to cover 4.2 and 4.3. 4.2, the mean value theorem. 4.3, how derivatives affect the shape of a graph. So 4.2, the mean value theorem. We start with the Rolle's theorem. Let f be a function that satisfies the following. Number one, f is continuous on the closed interval of L to B. Number two, f is differentiable on the open interval of A to B. Number three, f of A equals f of B. That means the endpoints have the same functional value, the same y coordinate in essence. Then there is a number C in the open interval of A to B such that f prime of C equals 0. These are some graphs that indicate those. Graphs of some typical functions that satisfy the three hypotheses are given. This is a horizontal line, covers that. This, in this case, if you connect A and B, I hope you see that if f of A equals f of B, when you connect the 2 points, that gives you a horizontal line. That's the idea, everybody. Okay, so f of A equals f of B in all cases. Let me try this color. In all cases, if you connect the 2 points, as you can see, you're dealing with a line that is a horizontal line. Every horizontal line, f prime is 0. In each case, it appears that there is at least one point, C comma f of C on the graph, with the tangent is horizontal, and therefore, f prime of C equals 0. That's the concept. So having said that, let's look at this example. We're going to follow the Rolle's theorem. Let f of x be x to the power of 4 minus 2x squared. Find all c in the interval of -2 to 2 such that f prime equals to 0. And reminding you, Rolle's theorem has the following three criteria. Number one, f is continuous in the closed interval of A to B, differentiable in the open interval of A to B. F of A is equal to f of B. Then there is, this means there is a C, an element of A and B such that f prime of C equal to 0. Those are the notations, and that's how we read. So what's happening here? What type of a function do we have here? It's a polynomial of degree 4. As you know, every polynomial is continuous and defined from negative to positive infinity. If it's continuous on negative to positive infinity because the polynomial, therefore it's continuous in the closed interval of -2 to +2. Same reasoning, it's a polynomial of degree 4. Therefore, it makes it differentiable from negative to positive infinity. Therefore, it's differentiable from -2 to 2. So we are going to evaluate the function at the endpoints. We're going to plug in -2. That means -2 to the power of 4 minus 2 times -2 quantity squared. And we're going to see what we get. I hope you recognize if you plug in 2, you also get 8, because this is 16. This is 4 times -2. So let me just write it underneath. So this becomes 16. This becomes +4 times -2 is -8. So no matter what, it's 8. So we have the first one, the second one, and the third one. Therefore, there must be a number such that f prime is 0, somewhere in between -2 to 2. So what do? We find f prime. So f prime of x, 4x cubed minus 4x, and we set it equal to 0. So to solve this, we're going to factor the 4x out. We get 4x times x squared minus 1. As you know, either x is 0 or x squared is 1, which gives you plus minus 1. So there are three answers. So according to the Rolle's theorem, there must be at least 1 point where that works. Now you have to make sure you look at those that are in between from -2 to 2, and they happen to be all in between. Thus, in the interval of -2 to 2, the derivative is 0 at each of these x values. So there are 3 points. So if you were to graph, the graph of f of x equals x to the power 4 minus 2x squared looks something like that. This is number 8, right? I mean the y coordinate at -2. Same thing at +2. So that means if you connect them, it becomes a line which is parallel to the x-axis. It's a horizontal line. That's the meaning of it. F prime is 0, and that's what this is all about. So at -1, at 0, at 1. So over here, that means here and here. So you can see that we have lines parallel to the x-axis with y prime being 0 in all those cases. So a quick recap. If a question like this is given, number one, you have to justify continuity. Number two, you're going to look at differentiability. Number three, you look at the two endpoints, make sure they are equal. And then you differentiate z equal to 0, find the points of interest. Sometimes they just want the x, sometimes they want x and y coordinates. So that means they want a pair. So I'm going to answer it accordingly. The mean value theorem, let f be a function that satisfies f is continuous on the closed interval of a to b, so far like Rolle's theorem. Number two, f is differentiable on the open interval of a to b, just like the Rolle's theorem so far. Then there's a number c in a, b, the open interval, such that f prime of c equals f of b minus f of a over b minus a. So I want to discuss the issue here and what it means. So you have some function a and b. So that's what we have. If you connect the 2 points, it gives you some sort of a line. And if you look at this line, the name is, it's a secant line. Any curve, when you pick 2 points and connect them, the line it creates is called secant line. There is a line parallel to a secant line. That's the meaning of this. That means there is a line such that its slope is equal to what we just see, the slope of a secant line. We are looking for that point. So this has coordinates a f of a. This has coordinates b f of b. So what is this? Rise over run. This is the slope of this line, which is known as the secant line. F of b minus f of a over b minus a represents the slope of the secant line. There has to be some line in between a and b that is parallel to that. So that point, at that point, when you find the derivative, you set it equal to 0, gives you the point. That's the idea. So this is the point we are looking for. F of b minus f of a over b minus a represents slope of a secant line. In other words, there is a point P where the tangent line is parallel to the secant line AB. This is the secant line AB. So the mean value theorem is as follows. Number one, f is continuous on the closed interval of a to b. Number two, it's differentiable on the open interval of a to b. Then there is a number c in the open interval such that f prime of c is f of b minus f of a over b minus a. By the way, if you do the cross product here, in other words, this is f prime over 1, multiply these two, multiply these two. Then you get f of b minus f of a is f prime of c times b minus a. So the mean value theorem, it can be written in this format or in this format, makes no difference. So now you really have to realize Rolle's theorem is a special case of the mean value theorem. So that's pretty straightforward. That is the Rolle's theorem, special case of a mean value theorem. All right. So here's an example. The mean value theorem, given f of x equals 5 minus 4 over x. Find all c in the interval of 1 to 4 such that the slope of a secant line equals the slope of a tangent. Well, first and foremost, I hope you realize this is a rational function. Everybody can graph it nice and easy. You can write 5 minus 4 over x or 5x minus 4. If you were to combine them, not that you have to, but this is the same as 5x minus 4 over x, okay, just in case. So I'm assuming everybody can graph it. So you have the graph, 1 and 4. So we're going to locate 1 and 4. Connect them. This is the secant line. And according to the mean value theorem, there is somewhere in between, there is some point in between that we can draw a line parallel to that. So we are looking for that point. That's it. That's the question. So let's discuss the criteria. What type of a function do we have? We have a rational function. As you know, the domain of rational function is all real numbers except what makes the denominator 0. So all real numbers except 0. So if the function is continuous from negative to positive infinity except at 0, that means negative infinity to 0, union 0 to infinity, then it is continuous in the closed interval of 1 to 4. So f is a rational function. And x can't be 0. That's the domain. So f is continuous from negative infinity to 0, union 0 to infinity, and therefore it's continuous in the closed interval of 1 to 4, and of course differentiable. Also remember, when we say a function is defined in its domain, and we mention the domain, then in the domain, in the entire domain, the function is continuous as well as differentiable. Although differentiable means continuity, not the other way around. Okay? Sometimes you may have a sharp corner. So having said that, we are going to evaluate f prime of c as f of b minus f of a over b minus a. That means f of 4 minus f of 1 over 4 minus 1. So if I plug in 4 here, I hope you see this 4 over 4 becomes 1, 5 minus that is 4. And f of 1, if I put 1 here, I get 4, 5 minus 4 becomes 1. It so happened f prime is equal to 1. Now let's find f prime of x. Now to find f prime of x, let's look at this one and write it as 5 minus 4 x to the power of minus 1. So if you want to differentiate it, then f prime becomes -4, -1, x to the power of -2, or simply 4/x². Okay. So we are looking for some point such that the derivative 4/x² equals f prime of c, so equals 1. So set this equal to 1 and solve it. This means x squared, let's just do the cross product, right? That means x² is 4, x is plus minus 2. And in the given interval of 1 to 4, only 2 works, okay? Why? Again, because -2 is not in the given interval. By the way, at -2, just for the sake of argument, also there's a line, there's a tangent line parallel to the secant line, but they just want it from 1 to 4. So I hope everybody's comfortable with the concept. All right, I'm going to use the mean value theorem in this case. Suppose f prime is between 3 and 5. So 3 is less than or equal to f prime of x, less than or equal to 5 for all x. Show that f of 8 minus f of 2 is between 18 and 30. In other words, 18 less than or equal to f of 8 minus f of 2, less than or equal to 30. So to do that, we have to pay attention to what's going on with the mean value theorem. So we have f of b minus f of a in the numerator, b minus a here. So this is f of b minus f of a, if you want to use that, which makes a2 b8. It's a matter of comparison. So f must be continuous in the closed interval of a to b2 to a, differentiable in the open interval of a to b. And why is that? Because they said so. They said f prime is always between 3 and 5, which means f prime exists. When they give you the value of f prime, that means f prime exists, no matter what. That means the function is differentiable. And if a function is differentiable, it's continuous. Therefore, the mean value theorem applies. Again, I'm going to emphasize that f prime is between the two values for all x. So if that is the case, f prime of c is also between 3 and 5. And f prime of c is f of b minus f of a over b minus a. So f prime is between 3 and 5. So we keep 3 and 5, and if f prime is between 3 and 5, f prime at any point, for example, f prime of c is the same thing. And so f of b minus f of a, f of 8 minus f of 2, and b minus a is 8 minus 2. Obviously, 8 minus 2 is 6, and we are going to multiply everything. If I put a bracket and number 6 here, that means I'm multiplying everything by 6. This becomes 18, and this becomes 30, and this goes away. And believe it or not, that's the proof, because we wanted to show that f of 8 minus f of 2 is between 18 and 30, and we just showed that. All right, how derivatives affect the shape of a graph theorem. A function is increasing where f prime is positive, decreasing where f prime is negative. So increasing looks like almost aligned with a positive slope. Decreasing looks like almost aligned with a negative slope. A critical point, C of a function, is a point for which f prime is 0 or f prime does not exist. A relative max or relative minimum is a critical point at the top or bottom of an interval of a graph. That means peaks and valleys. A function is concave up where f double prime is positive, which means f prime is increasing. So it can hold water in essence. Remember that. A function is concave down where f double prime is negative. That means f prime is decreasing, cannot hold water. An inflection point, short IP. An inflection point C is a point where concavity changes. Inflection points occur where f double prime is 0 or f double prime does not exist, DNE. So as you can see here, this is concave down, concave up, and at this point where concavity changes, we call it a point of inflection. So to elaborate on that, concave up, the graph of f of x lies above all its tangent lines on an open interval. Concave down, the graph of f of x lies below all of its tangent line on an open interval. So if we look at these two cases, concave up, above we through a one tangent line, this one is below. So that's what it indicates. Furthermore, notice what's happening here. If we draw two, in this case, we have a tangent line, okay, line segment, and this one has a larger slope. So f double prime is positive and f prime is increasing. Okay, so remember the slope, in essence, f prime evaluated at a specific point becomes the slope is increasing. On the other hand, this is negative, so is this one, but this is steeper and therefore more negative. So it makes perfect sense here. Also, in this case, f double prime is negative, concave down, and f prime is decreasing. Look at this one. This has a negative slope. This has more negative slope. This has a positive slope, but this has less positive slope. So f prime is decreasing. And finally, a point P on a continuous curve f of x is an inflection point if f of x changes concavity there. As you can see, concave down becomes concave up. That point, concave up becomes concave down, point of inflection. So that's as far as the definition is concerned. Extreme values of a function are created when the function changes from increasing to decreasing or decreasing to increasing. As you can see here, the function is increasing first and decreasing. And the peak is an extreme value. More specifically, it's a local max. Here, first is decreasing, then increasing. It's an extreme value. It's a valley. It's a local mean. Here, decreasing, increasing, decreasing. As the change occurs, as we change from decreasing to increasing, we have an extreme value. This is a local minimum. Here, we have a local maximum. Over here, increasing, decreasing, increasing, decreasing. So increasing to decreasing local max, decreasing to increasing local mean, and that is telling you how to find local max and mean as the change occurs from increasing to decreasing gives us the local maximum. As the change occurs from decreasing to increasing gives us a local minimum. So that's pretty obvious. This is extreme value, so is this one and this one. So a function is increasing where f prime is positive and decreasing where f prime is negative. And by the way, it can be proved by the mean value theorem. Okay, we just went over the mean value theorem, and so remember the concept of a mean value theorem. You have a curve, you connect 2 points, you draw a line, and it becomes a line known as a secant line. Okay, there is somewhere in between that the tangent line is parallel to that. So If f is continuous on the closed interval of a to b, f is differentiable on the open interval, then f prime must be equal to f prime of c. There must be some point c such that f of b minus f of a equals b minus a, or the cross product, as you recall, f of b minus f of a is the product of these two. That means the same thing. Now, also remember, increasing means as x increases, so does y. That's the easiest definition we can think of. That's the meaning of increasing. X gets larger, so does y. Decreasing is the other way around. Means as we move from left to right, always x increases. But what happens to the y? Increases, increasing, decreases, decreasing. Okay. So let b be larger than a. Generally speaking, we choose b to be on the right side and b is larger than a. Okay. Now, if f prime happened to be positive, okay, then f prime of c is positive, right? If f prime of x is positive, that means f prime is positive all the time. F prime of c is positive. And so it makes this fraction positive. Now, if b is on the right, then b minus a is positive. And if this is positive, if a fraction is positive, and we know the denominator is positive, the numerator must be positive also. Okay, since b is larger than a, f of b must be larger than f of a, and that makes it increasing. Believe it or not, that was a proof by the mean value theorem. All right, what is the first derivative test? Y prime or f prime is positive, then curve is rising, as I mentioned, increasing. If it's negative, it's falling or decreasing. So what do we create here? A peak, local max. But if it's the other way around, first is negative, it's falling first. And if f prime becomes positive afterwards, curve is rising afterwards, again, it creates an extremum, and that's a local minimum or a value. So y prime or f prime equals 0 or does not exist. Those are possible locations of max and mean. And we use sign graph for the test. Concavity test. All right. What's happening here? Y double prime equals f double prime is positive. The curve is concave up. So we went over the synopsis of that. Now we are elaborating. If it's negative, curve is concave down. If it's 0 or doesn't exist, those are possible inflection points. A function is concave up where f double prime is positive. That means f prime is increasing, and concave down where f double prime is negative or f prime is decreasing. How do we find it? Again, sign graph. Now, a lot of times students may mix up the concavity test with the second derivative test. Second derivative test does half of the first derivative test. First, you have to find f prime set equal to 0 and find the critical point or points. Then you evaluate f prime at those critical points. If you plug in and you get negative, graph is concave down, looking like that, we have a local max at that critical point. If it's positive, graph is concave up, okay, we have a local minimum because it looks like that. So it's a wonderful tool for applications, not for graphs. Because when I get to graphing, I want to remind you of a couple of things from algebra, pre-calculus. Recall, the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches the positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. F of x is a sub n, x to the power of n, plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0. And the graph ultimately looks like the leading term, y equals a sub n, x sub n. That's the idea. So having said that, if we look at this, when we are dealing with an even power, the leading term is of even power, looks like one of these two, odd looks like one of these two. This looks like y equals x squared, y equals minus x squared, y equals x cubed, y equals minus x cubed. So the leading coefficient a sub n is positive. The leading coefficient a sub n is negative. This looks like x squared opens up. That means the n behavior belong to the first and second quadrant. That means when x goes to positive or negative infinity, in both cases, f of x goes to positive infinity. When the leading term is negative, f of x looks like minus x squared. It goes down to the third and fourth quadrant. That means x goes to positive or negative infinity, makes no difference. F of x or y goes to negative infinity. However, when it's of odd power, either looks like f of x equals x cubed in the case of leading term. In this case, leading term coefficient is 1 positive. If it's negative, looks like minus x cubed. So in this case, x goes to infinity, x goes to infinity, y goes to infinity, x goes to negative infinity, y goes to negative infinity. In this case, it's the other way around. Behavior near a zero, multiplicity of zero, in this case, x minus c to the power of m is m. If m is odd, f crosses the x-axis at c0. If it's even, f can't cross the x-axis at c0. Okay. By the way, p or m, depending upon the text, it crosses, but this one it can't. Also, the higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function. So I wanted to remind you of this stuff, so when we graph, it makes a perfect sense to you. All right, we want to graph this function. So I'm going to remind you the synopsis of what we need to do to graph. Number one, steps to curve sketching. In addition to algebra and pre-calculus step, that means find the intercepts, know what the end behavior happened to be, and then you add relative extrema, inflection points, and so forth. So for now, we are going to ignore the rest, and I'm going to show you how to graph this without the calculus. It is possible to do so, but with calculus, it looks a lot better. So how would you deal with that? Number one, we are going to factor x, or in this case, minus x, in case the second piece can be factored. So I take a negative x out, and I get x squared minus x minus 1. I want to set this equal to 0 because I'm interested in finding the intercepts. As I set this equal to 0, this becomes 0, and this one I need to use the quadratic formula, okay, which is minus b plus minus a squared of b squared minus 4ac over 2a. And in this case, if you look at this, a is 1, b is negative 1, and c is negative 1. We're going to plug in. This is negative, negative plus 1. This is 1 plus 4, so square root of, so it's 1 plus minus square root of 5 over 2. And that means we have the following three intercepts: 0, 0, 1 plus square root of 5 over 2, comma 0, 1 minus square root of 5 over 2, comma 0. Please understand this one is both x and y intercept. Otherwise, you must find the y intercept as well. I can't emphasize this enough. Now, for the sake of graph, again, I'm going to write 1 plus square root of 5 is almost 1.6, and this is almost negative 0.6. So we have 0, 0, 1.6, negative 0.6. And notice this is a function of degree 3, and it has 3 zeros, so all of them will cross. Okay, so behavior near an x-intercept. Minus x cubed tells us the end behavior, gives us the second and the third quadrant. So it goes down like this, hits this one, comes back up, and it's this one. Now, without calculus. We don't know where is the local mean, local max, but this is a rough sketch. Again, I just wanted to show you it can be done without a calculus, but it's not as precise, of course. Now, so the next step is to use calculus. So what is this step? Find relative extrema, max and mean, and intervals where the function increase and decrease by setting f prime equal to 0 and solve for x and make a sign graph. And the next one is finding inflection points at f double prime equals 0 and so on and so forth. So let's start with relative extrema. Let me erase my work. And now we are going to go with critical points. We are going to find f prime of x. We go back to this one, negative 3x squared plus 2x plus 1. We are going to factor the negative out. And because this is 3, you have no choice but to go with 3x and x. And then this is negative 1. One is positive, one is negative 1. And you have to check the middle term. And notice right now, this middle term, this is negative 3x. This is a positive x. They do add up to minus 2x. So that's how you find it. I'm going to erase my work again because we need the space. And so either x is 1 or negative 1/3. So as far as the first derivative test is concerned and the sign graph, you go with a number line from negative to positive infinity. And you put these two numbers from smallest to largest. And at negative 1/3, f prime is 0. At 1, f prime is 0. And you find TPs. I'm going to say TPs, short for test points. So obviously in between, the easiest would be 0. This is minus 1. This is maybe 2. What I want you to know is that this is degree 2 and has 2 answers. Therefore, they must alternate. Or take a look at the factor form. Each one has an odd exponent. So the easiest one is to find the 0. If I put the 0 here, I get plus 1. That means positive here. They will alternate. But if you have doubts, just plug in another number, maybe 2, and find out what's going on. In any event. So what that means is, again, let me erase my work. So let me throw in arrows. I put down arrow for negative, up arrow for positive. So it shows me easily that decreasing, increasing, this is a local mean. Increasing, decreasing, this is a local max. Local max at 1 and local mean at negative 1/3. 1, you have to find the pair. If I plug it back in here, minus 1 squared is 1 cubed is 1, so minus 1 plus 1 plus 1 is just 1. So local max is 1 at 1, 1. And local mean, I have to plug in negative 1/3. So minus negative 1/3 cubed. That means negative 1/27 times negative is positive 1/27. This is positive 1/9 minus 1/3. And obviously 27 is the common denominator. So 1 plus 3 minus 9 is minus 5. So local minimum is minus 5/27 at 1 at negative 1/3 and negative 5/27. Now, furthermore, negative means decreasing, positive means increasing. So it's increasing from negative 1/3 to 1, decreasing from negative infinity to negative 1/3 union 1 to infinity. As you can see, the first derivative test gave us a lot of information. Now, the next step is to find inflection points. How do we do that? We find f double prime. So I wrote everything from the previous page. I wrote f of x, f prime of x, intercepts, max, mean, and the rest of them. And now I'm going to find f double prime, which is minus 6x plus 2. Set this equal to 0, and you get 1/3. You go with the number line from negative to positive infinity. You put the number here, and at this point, f double prime is 0. As you can see, it's of degree 1 and has one answer. So basically, if you look up a test point, TP, to the left of 1/3 0, to the right 1, just try 0. If I put 0 here, I get positive 2. So positive, they will alternate. So that means positive means concave up from negative infinity to 1/3. And negative means concave down from 1/3 to infinity. And because of the change at 1/3, we have an IP, inflection point. So what is the wall coordinate? We have to plug in into f of x. So f of 1/3 is minus 1/3 quantity cube plus 1/3 squared plus 1/3. This is 1/27. This makes it negative. 1/9, 1/3. And again, 27 is the common denominator. So if this is 27, this is 3. If this is 27, this is 9. 3 and 9, 12 minus 1 is 11. So 11/27. That's the inflection point. Practically, we are done. I'm going to write everything we have in a summary table always. That is helpful. We're going to start with the x-intercept at 0, 0. Then again, 1 minus square root of 5/2. We're going to go with negative 0.62 somewhere here. 1 plus square root of 5/2. We're going to go with the approximation about 1.6. This is 1.6 about here. Maximum at 1, 1 is here. And because it's a maximum, we draw an arrow, meaning it can't cross that. IP, we're going to go with the decimal representation for the sake of a graph, 0.3, 0.41, 0.3, 0.41 is somewhere there. And minimum, again, we're going to go with the decimal representation, minus 0.3, let's say minus 0.2, somewhere there. And because it's a minimum, again, we draw a double-headed arrow, and minus x cubed gives us the end behavior, and that's the graph. As you can see, the function is concave up here, concave down here, okay, decreasing, increasing, decreasing, local mean, local max, all the intercepts, everything is given with details. What about this function? Again, this can be done by hand, just the way we have done it in the previous page, but let's just continue with this methodology by finding intercepts. So first, let's set it equal to 0. And to do so, I'm going to factor either x squared or half of x squared. If I factor half of x squared times x squared minus 2, either this one is 0, that means x is 0, or x squared equals 2. X, let me just write that. This means x squared equals 2, or x is plus minus square root of 2. So there are 3 answers. 0, 0, because we got the 0 here, minus square root of 2, 0, square root of 2, 0. And by the way, 0, 0, this one has multiplicity 2. In other words, if I were to graph this using algebra, I pay attention to that, okay? Just in case. All right. Let's move on with relative extrema by finding f prime of x and the first derivative test, which means I'm going to differentiate this. 1/2 times 4 is 2, 2x cubed minus 2x. To set this equal to 0, I'm going to factor the 2x out. So 2x times x squared minus 1. And x squared minus 1 is x plus 1, x minus 1. So there are 3 zeros. X is 0, x is negative 1, x is positive 1. There are 3 zeros, everybody. So we are going to draw a number line from negative to positive infinity. And we're going to put those numbers in order from smallest to largest. Negative 1, 0, 1. At each and every one of those, f prime is 0. And we're going to use a TP or test point. Now, for example, here is -2. Here's minus 0.5. Here's positive 0.5. Here's 2. And understand what happens. We go back to f prime, and f prime has degree 3, or if you look here, the exponent is 1, 1, 1. That means they will alternate. That means that you don't have to evaluate all of them. One of them you evaluate, and the rest of them will alternate. So let's plug something in, just for the sake of argument. For f prime, if I put 2 here, 2 cubed is 8 times 2 is 16. This is 4. So 16 minus 4 is positive. So this is positive, and they alternate, negative, positive, negative. This positive should be up there, everybody. And so I'm going to put the arrows. They will help me see what's going on. Down arrow, decreasing, negative, up arrow, increasing. Okay. And therefore, we are going to find over here at negative. Okay. So decreasing, increasing, this is a local mean. Increasing, decreasing, local max. There's one local max. Decreasing, increasing, local mean. There are two local minimum. So we're going to plug in both of them into original function, and it doesn't matter which one, because both have degree even, they result in the same thing. So this is 1, half of it is 1/2, this is 1, so 1/2 minus 1 is negative 1/2. So local minimum is negative 1/2 at x equals plus minus 1. That means the following pairs. Now, local max is 0 at 0. If you plug in 0, you get 0. And that's exactly what we had here, the intercept and that multiplicity 2, that is referring to one of those two. So having said that, notice, let me just erase my book so to make it easy. This negative means decreasing. So it's decreasing from negative infinity to negative 1. Union 0 to 1. And it's increasing from negative 1 to 0, union 1 to infinity. So let's write that. Okay, so local maximum, and then decreasing, increasing. Now, this is the information from the previous page, and we want to add the inflection point. That means we are going to find f double prime. So everything from the previous page, f of x, f prime of x, intercepts, the rest of them. So this one, we are going to differentiate, which means f double prime is 6x squared minus 2. Setting it equal to 0 requires factoring. We're going to factor the 2 out. 3x squared minus 1 is 0. That means 3x squared is 1, x squared is 1/3, and therefore x is plus minus 1 over square root of 3. So we are going to go with the sine graph. From negative to positive infinity, we are going to put the x here and f double prime here, minus, and we put these two numbers from order from smallest to largest. You don't even have to know the decimal representation to know this is smaller than this. And in between, if you want to go with the TP, obviously the easiest number in between would be 0. And over here is negative 1, over here is positive 1. And because there are two answers, this was degree 2, they will alternate. Just evaluate it at 0. So if I plug in 0 here into f double prime, I get negative 2. I just want the sign negative. So they will be a positive on the other side. So what does it mean? So Negative means concave down from here to here, from -1 over square root of 3 to 1 over square root of 3. And concave up from negative infinity to negative 1 over square root of 3 union 1 over square root of 3 to infinity. Because of the change, positive to negative means concave up to concave down and concave down to concave up. Both points represent IPs. So if they are the IPs, you need to know the y coordinate. We're going to put it back into the original function. Let me erase my work. So we put this back into the original function. 1/2 plus minus 1 over square root of 3 to the power of 4 will be the same, minus plus minus 1 over square root of 3 to the power of 2. I hope you recognize this one as 1/3. Therefore, this one is 1/3 squared, or 1 over 9. So 1 over 18 minus 1/3. Because this is 1 over 18, we're going to change this to 6 over 18, and we get minus 5 over 18. And so the IPs are at these two pairs. So pretty much we have everything. Let's write the summary here for the sake of graphing. So square root of 2 is about 1.41. So here's 1, here's 1.41, here's -1, here's negative 1.41. So those are the two x-intercepts. We have the 0, 0 as both x-intercept, y-intercept, as well as maximum. So that's why we put the double arrow, meaning it can't cross that if we were to graph. The IPs, those are the exact answers. We're going to go with the approximation for the sake of graph. So let's say minus 0.6, minus 0.3. So somewhere here roughly. And positive 0.6, negative 0.3 somewhere there. Then the minimum at -1, -1/2. So -1, -1/2, and +1, -1/2. This one, and we put an arrow. This one, and we put an arrow. Let's go back to original function. 1/2 of x to the power of 4. X to the power of 4 looks like x squared because the leading coefficient is 1/2 and it's positive. So we are looking at the first and the second quadrant. So the graph looks like that. Notice the function is decreasing, increasing, decreasing, increasing. The function has a local minimum here, local maximum here, local minimum here. The function has an inflection point. We have a function which is concave up, then it becomes concave down, then another inflection point, concave up. Everything that you want is there. It pretty much represents everything you want for a graph. I want to sketch this graph. F of x is x minus 2 to the power of 2/3 plus 1. And let's see how we do that. First and foremost, I want to tell you the type of function you have, and therefore I want to show you the pre-calculus part. So I'm going to rewrite this as cube root of x minus 2 quantity squared plus 1. So it's important to understand this is cube root of x minus 2 quantity squared plus 1. So the basic function cube root of x is the starting point, and we should know it looks like this, where the domain is all real numbers. We have the x and y intercept at 0, 0, and that's the starting point. The next one is to look at cube root of x minus 2, which means it's the same function, but it's been shifted to the right by 2 units. So we are going to move this to the right by 2 units. Looks like this. So 0, 0 moves to 2, 0. The next step is to graph cube root of x minus 2 quantity squared. What happens now when we do that? The effect of raising a function to a power, it makes it larger. The positive side makes it larger. The negative side, if the exponent is even, will become positive and larger. So that's what we get. So the positive side simply becomes larger. The negative side flips over, becomes positive, and basically we have the same x-intercept at 2, 0. Finally, plus 1 means shifted up by 1 unit. So the same function comes up by 1 unit. At 2, 0, 0, 0, 2, 0, 2, 0. Now it has the coordinates 2, 1. So this is transformation we should be familiar with as far as pre-calculus is concerned. But let's graph it here with more detail. So this is the function, and we are going to find f prime of x, so on and so forth, see how we deal with that, everybody. Okay, so we want f prime of x, which means we are going to differentiate this one 2/3, x minus 2 to the power of negative 1/3 times the derivative of the inside, which is 1. We're going to rewrite this by writing this to the power of positive 1/3, which becomes a cube root at the bottom. Remember what we want. We want to find the critical points where f prime is 0 and f prime does not exist. So f prime 0, a fraction is 0 when the numerator is 0. The numerator being any number, positive, negative, small, or large, makes no difference. There is no solution. F prime does not exist. The denominator equal to 0, and x becomes 2. Therefore, you go with a number line from negative to positive infinity. You put this number here, and at 2, f prime does not exist. You go with the test point. Obviously, to the left of 2, you go with 0. To the right is 3. And if you plug in 0, plug in 0 here, you get minus. And cube root of negative is negative, so this becomes negative. If you put 3 here, becomes positive. Cube root of a positive number is positive, and so on. So everything is positive. This means, let's throw in arrow down and arrow up. This means decreasing. This means increasing. Okay. And so the function is decreasing from negative infinity to 2, increasing from 2 to infinity. So 2 is where the local minimum occurs. So if we plug in 2 back to into the original function, whether here or here makes no difference. This goes to 0, so the answer is just 1. So local minimum is 1 at x equals 2. In other words, that's the pair 2, 1. There is no local max. So that's pretty straightforward, everybody. And as I mentioned, it's decreasing from negative infinity to 2, increasing to 2 to infinity. The next one is the inflection. How do we find the inflection point f double prime? How do we find f double prime? Let's go back here. We're going to differentiate it again. In order to find f double prime, 2/3 times negative 1/3, negative 2/9. X minus 2 to the power of what? Subtract 1 minus 4/3. The derivative of the inside is 1, has no bearing. You're done. We're going to rewrite this by taking this down here, make it x minus 2 to the power of positive 4/3, write it in this format. Now, you may recognize this is always negative except at x equals 2. Why is that? If you look at the denominator, except 2, if you pick any number Cube root becomes positive or negative, doesn't matter. The exponent 4 makes it positive. This is positive. 9 is positive. This negative 2 makes it always negative. So it's always concave down. Do we write it from negative to positive infinity? Absolutely not. We write from negative infinity to 2, union 2 to infinity. Now, if you wanted to go with the sign graph, and I highly recommend you don't need to, everybody. You can say f double prime equal to 0. Again, this can't be because it's a number. Doesn't exist. The denominator is 2. And you do a sign graph to the left of 2. Obviously, you pick 0. If you plug in 0, you get minus 2. Cube root negative 2 becomes positive with the 4, becomes negative in both cases. You can go this route if you insist to use the sign graph. You don't have to if you recognize it's negative always, with the exception that was mentioned. So now what we have, everything that we did in the previous pages, we are going to write the function in two formats, okay? And where the function is increasing, decreasing, concave down, the minimum that we found the previous page. And now we want to find the intercept. So one easy intercept is the y-intercept. Plug in 0 here or here. If I plug in 0, I get minus 2. Squared, I get 4. Cube root of 4 plus 1 precisely. That means 0 cube root of 4 plus 1. For the sake of graph, we're going to go with the rough estimate of cube root of 4 plus 1 is 2.5874, 2.6. There is no x-intercept. Why not? Let's find out. Okay, in order to find x-intercept, you set the y or f of x equal to 0. I'm going to move the 1 becomes negative. Then I'm going to raise both sides to the power of 3 because it's a cube root. Left side comes out as x minus 2 squared. Right side is minus 1. So we are claiming x minus 2 squared is negative 1. As you know, there is no solution because this is being raised to the power of even positive. Worst case scenario is 0. Okay. So there is no solution. It will never be negative. There is no x-intercept. And now we want to sketch the graph. So we're going to put everything together. What do we have? We have the y-intercept and the minimum. It is really important to put a few easy points. I'm going to start with easy points. For example, 1. If I put 1 here, everybody, I get negative 2. Cube root is negative 1, squared is positive 1, and 1 is 2. Another easy point, 3. If I put 3 minus 2 is 1, cube root is 1, squared is 1, and 1 is 2. So 3, 2. And there are more points. Negative 1 I picked on purpose. You need a calculator. But for example, negative 6. With negative 2 is minus 8. Cube root is minus 2. Square root is 4 plus 1 is 5. 10 minus 2 is 8. Cube root is 2. 2 squared is 4 and 1, 5. So those are easy points. And all we have to do, plot the pairs. And we're going to start with this one is 0, let's say 2.6. So this is 5, 1, 2, 3. So somewhere in between there. So that's the first one. 1, 2. So this is 1, 2 here. 2, 1, 1, 2, 1 up here. 3, 2, 1, 2, 3, 1, 2. And by the way, that's the minimum. What else do we have? Minus 1, 3.08. Minus 6, 5. This is minus 5. So minus 6 is here. 5 is up here. 10 is here. 5 is up here. Putting them all together. And we notice the function is decreasing here, increasing here, concave down, also concave down. So this is another point of inflection because concavity does not change.